So let me now switch gears and introduce our first speaker, Professor Bernhard Müeller of the Monash University in Australia. Professor Mueller is one of the world leading experts in the computational physics of very complex astrophysics phenomena, in particular the core collapse supernovae. So he did his PhD at Munich and was a postdoctoral scholar at the Max Planck Institute in Garching, and was a faculty fellow, a university research fellow at the Queen's University of Belfast before joining the faculty of Monash. He has a very large number of very impactful publications, original publications to his credit. And he's also very active in not only advancing the science, but also communicating his science. He has authored several very impactful reviews on the field of computational astrophysics, in particular core collapse supernovae, which are very widely appreciated by the community. So I'm very pleased to invite Professor Mueller for giving this first set of lectures on stellar evolution and collapse. Professor Mueller.
Gee, thank you very much. This was a very kind introduction, and it's a great pleasure to be here and lecture before such a huge audience on campus and off campus. I sort of regret that I can't be there in person. And I should basically probably preface my lecture by saying we should all be very much aware of the challenges of this hybrid format. We still want to make this hybrid format as interactive as possible. That is probably something of an experiment, but we'll see how it goes. What I'll do is I'll try to maybe stop every few minutes for questions. People might also put questions in the chat, and then we can somehow ensure that we can catch up with questions in between and make this reasonably interactive. I do encourage all of you very much to ask questions, because I'm aware I'm talking probably to a very diverse audience. So some of you in the audience may know more about the evolution of massive stars than I do. If you feel there's a discussion point that you want to raise because the lecture doesn't address it in as much detail as you'd like to hear about, then please let me know and interrupt. Yes, and also interrupt if someone feels things are going over their head. I hope I'll be able to take a step back and walk you through any obstacles. It's always a bit of a challenge to pitch a lecture correctly if you have a very broad audience. So let's just work together and try and make it happen. Usually the lecturer gets credit for the lecture, but the lecture is really always an interactive experience where the audience equally contributes. So please do so. So we're going to address in this series of lectures the problem of the explosions of massive stars and how they form compact objects, what we can learn about these stars with all kinds of observations of the explosions themselves in electromagnetic radiation, in multi-messenger observations, neutrinos, gravitational waves, indirectly through their remnants and so on. And of course, we should start this with the theory of how massive stars actually get to explode. So the first lecture will be concerned with the evolution of massive stars. This is, I should say, the topic that I'm least expert on in this series of lectures, but I hope you nonetheless get something interesting out of it. If you're interested in digging deeper, there are a variety of good review papers on the stellar evolution of massive stars. The one that I'm going to rely on the most is the 2002 RevMod Phys paper by Woosley and collaborators. If you are able to study that and have understood that, then you are probably an expert in stellar evolution. All right, so let's start simply by reminding ourselves of what the stellar structure equations are, so how stellar evolution works physically. And if you haven't done any course on stellar structure and evolution before, you can at least glean from this brief discussion the basic principles. So the structure and evolution of stars is really governed by a set of conservation laws and a few set of rate equations. So stellar structure is governed on the one hand by the continuity equation of hydrodynamics, so a law for the conservation of mass. In most phases of the lives of stars, it's governed by an equation for hydrostatic equilibrium. There may be some exceptions to that, very dynamical phases where we actually need to treat this as a real fluid dynamics problem. We'll need an equation for energy conservation that tells us, based on where energy goes in by nuclear burning and where it goes out by photon radiation at the surface, or by the emission of neutrinos in deeper layers, what temperature structure the star maintains. We'll need some equations to tell us how energy flows within the star. So energy within the star may be transported by different means. It may be transported by the diffusion of photons. It may get out by cooling due to the emission of neutrinos, or it may be carried around by fluid motions, by convective motions, or other kinds of hydrodynamical instabilities. And you need effective equations for that. And finally, of course, you'll need, since stars are powered by nuclear fusion, you will need equations for the rates of change of the composition, quantified by what we know as mass fractions. So how many baryons of a given, what fraction of the baryons in a given small volume of the star is locked up in a certain element, carbon, oxygen, helium, whatever. So rate equations that tell us how these mass fractions change due to nuclear burning. And based on that, based on the release of binding energy associated with that, of course, we also get the new energy input into internal energy by nuclear fusion or dissociation in some cases. Now, we also know that stars generally rotate. Sometimes they may rotate slowly enough for us to neglect that, but generally they do rotate. So in the most general case of the evolution of massive stars, you actually include the transport of angular momentum within the star, which can happen by various physical processes. We'll go into that. That's sort of a step a little beyond what you learn in standard stellar structure courses. So we'll leave that to a little later. And all these equations that come from these physical principles will be underdetermined in the sense that we need something to close that system, an additional relation, the equation of state that tells us what is the pressure in terms of density and temperature and composition. Now, for practical purposes, almost all stellar evolution models that evolve stars over secular timescales, so significant fractions of their lifetime, need to be evolved under the assumption of spherical symmetry. Yeah, treating them in full multi-dimensions is too expensive. Some attempts have been made to construct two-dimensional stellar models, axisymmetric stellar models, but these are still not fully general. They're restricted to certain evolutionary phases. And as far as the evolution of massive stars from formation until the collapse as a supernova are concerned, we still rely on one-dimensional stellar evolution models. There was a question in the chat there, what does secular mean? So secular means on much longer timescales than dynamical timescales, over timescales comparable to the age of the star. In Latin, the word seculum is the word for century or age or era. That's where this comes from. Now, for selected phases of stellar evolution, we can, however, nowadays perform very short multidimensional simulations of important dynamical phases. That's going to be a topic a little later in this lecture. Now, these are the physical principles, and I think some of you have probably seen what this looks like in terms of equations. We're not going to focus so heavily on the equations. The physical principles are really important to understand, and you can formulate these physical principles in slightly different language. So whether you express all the structural thermodynamic variables as a function of the enclosed mass inside a certain mass shell, or as a function of radius, they look slightly different, but that does not really change the physics. Yeah, and in the common form that you might find in a stellar evolution textbook, you would conveniently express all these physical expressions in terms of the enclosed mass inside a certain radius in the star. That has the advantage that this gives you what is known as a Lagrangian coordinate system. So a certain shell, as it moves, as it might move in radius, always stays at the same mass coordinate, and that makes the calculations, or many calculations, a bit easier on the computer. Yeah, and in that particular form, the equation of continuity for mass conservation looks like this. You can reformulate this also in terms of an equation for enclosed mass in terms of radius very easily. The equation for the hydrostatic equilibrium looks like this. If you reformulated that in terms of derivatives with respect to radius, you would simply find that hydrostatic equilibrium is given by the condition that the pressure gradient balances the gravitational force density. You'll actually play with this in the tutorials. Yeah. Then the equation for energy conservation is given like this. So what you basically say is you have source terms and sink terms for the local energy of a shell of your star, source terms from nuclear burning, the sink term from neutrino cooling, and then also some terms that account in this coordinate system for the compression of matter as the star expands or contracts. And those source and sink terms need to be in balance with the energy flux, that's the L here, the luminosity in photons that's flowing in and out of a certain shell. That's what this equation really expresses. So how fast energy flows, so the energy flux as a function of let's say, gradients of temperature and so on, that is expressed in another equation, which we don't need to go into too much detail. This is one of the more cumbersome formulations in standard stellar evolution textbooks. Suffice it to say, so in the limit of that energy is carried by photon radiation, you basically get a diffusion law that gives you the flux of energy in terms of the temperature gradient. And if energy is predominantly carried by convective motions, then this will look a little different. We're not going to go into the mathematics there, really. This is, I think, a bit too cumbersome. That would really need an entire lecture of its own. And the final set here, these are the rate equations for nuclear reactions. All right, now numerically, this is of course a very complicated nonlinear system of equations. So in general, those equations need to be solved by some numerical scheme. As I saw when I looked up the schedule, one of the mini projects is actually about working with real stellar evolution models to play with these equations. But for understanding how stars evolve to collapse, how massive stars evolve to collapse, why the more massive stars look different than the less massive stars, what is required for a star to end as a supernova explosion instead of a white dwarf. Much of that can already be understood if you boil down the stellar structure equations to simple scaling relations. So if you use, for example, the assumption that your pressure is given by something like a polytropic equation of state, where the pressure just depends on density, that can happen, for example. Let me just finish this, then I'll come back to a question in the chat. That can happen, for example, if the structure of your star is such that you have, say, more or less constant entropy throughout the star. That will give you a one-to-one relation between pressure and density. And there was a question before I move on in the chat about the stellar evolution equations. So there was this gradient, this nabla symbol here. What that actually means, that's a very strange thing. That's a very strange notation, really. This really just means a gradient of temperature with respect to, I don't recall, pressure or density in the limit of that energy is transported primarily by diffusion. So what this actually really stands for is a thermodynamic derivative of temperature with respect to other variables rather than some operator. It's just old-fashioned astronomical notation. This is actually not a gradient operator. It stands for a particular thermodynamic derivative. Yeah. Now there were questions about E in these equations, the epsilon here. Yeah, I think I may have briefly mentioned that, but it can't hurt to reiterate. The epsilons here are source terms. The first one is the source term of energy due to nuclear reactions. And the second one is a sink term due to the emission of neutrinos from the stellar matter. Not that epsilon, the one in the denominator. Where is it? Maybe it's actually not an, this one. So there's something here, there's a row here that might look like an E. So this is actually a row here in the denominator in the last equation, not an E. That's density, not an E. Okay. All right, so coming back to where we left off. So as I said, it's illustrative to, instead of just going ahead, plowing ahead and solving the stellar structural equations by brute force on the computer, to come up with some simple scaling relations if you assume that you have, for example, this polytropic equation of state, which you might justify by if your star has approximately constant entropy, and then boiling down these differential equations to what we often know as one-zone models. So we'd replace a derivative here with a difference of the central value and the surface value. So the surface value of pressure will be close to zero. And this whole thing here, for example, in the hydrostatic structure equation, would just be turned into central pressure over mass as an approximation for dp over dm, a very crude approximation, yeah, and so on. And again, I don't want to do very long-winded calculations here, so I left this actually for the tutorials. What you can then infer for the thermodynamic properties of the interior of your star is a very useful relation for the how stars of different mass will be placed in the phase space, in the parameter space, central temperature versus central density. And it turns out that there's a nice relation that T cubed over rho, both for a perfect gas equation of state and a radiation dominated equation of state, is proportional to, roughly proportional to mass squared. Yeah. And as with all of these one zone relations, it's a bit tricky to interpret what this means, because if your star, let's say later on, develops a distinct core and envelope structure, right? So you'll get on the red giant branch, for example, as the star expands, you get a distinct core in a very dilute envelope, then this relation might be better expressed for, let's say, the core of this stellar structure that is still described very well as a polytrope. And you might need to put in here the mass of a part of the core of a star instead of the entire mass of the star. So with all of these scaling relations, you always need to be a bit wary which quantities should actually go in there. That's where the physical intuition has to come into play. Yeah. So what we basically get is that this is a rough relation that temperature cubed over rho will be bigger for higher mass stars. And you'll also note actually that for radiation, if the entropy of the stellar matter mostly comes from radiation, that this thing here on the left-hand side is actually proportional to the entropy of the matter. So this means that as you start out, let's say on the main sequence, the stars of higher mass will be stars that have bigger entropies in their cores. And as you proceed through the evolution, if the entropy of stars were to remain constant, they'd always follow this T cubed over rho equals constant trajectory. Now, in reality, that is actually not really the case. So the entropy of the stellar cores changes a bit by nuclear burning and neutrino cooling. And of course, the stellar structure, as I hinted at, becomes more complex, right? So you can't treat the entire star as a polytrope anymore. And for this reason, the actual evolution of the central conditions in massive stars is described exactly by this relation, but still very closely so. Yeah. So you'll see if you follow two real stellar evolution models here of 15 and 25 solar masses, they'll basically follow this T cubed over rho trajectory approximately. And whenever burning stages are ignited, as denoted here, the trajectories become a little wiggly. They take a few detours. But overall, the evolution follows this trajectory quite well. Yeah. So these wiggles here, these changes come about for different reasons. On the one hand, the star might actually re-expand a bit. The core at least might re-expand a bit when you ignite a burning shell. During certain other phases, there might be sufficient, there might again be a significant cooling or so. That's what makes all these loops here. But just knowing about this these approximate trajectories, T cubed over rho equals constant, and putting that together with what you know about the regimes of the equation of state of stellar matter, already allows you to understand to a very large degree the fate of stars of various masses. Yeah, so if you, so I hope some of you have some little knowledge of the regimes of stellar matter already. So can quickly walk you through this. So what you'd find if you consider the various mention of the different elements. Okay, let's go back to this question actually before we move on to this diagram where we put the t cubed over rho trajectories in the and map them into the equation of state regimes. There was a question here in the chat about the different elements mentioned here. Yeah, so these denote the points in the life of these two stars where a certain burning phase is ignited in the core. So this is where hydrogen burning is ignited, helium burning, carbon burning, and so on. Yeah. All right, so let's go back and or go forward and map these approximate trajectories into the regimes of the stellar equation of state. So to consider the regimes of the stellar equation of state of stellar matter, what we need to know is basically this. So if you go to the regime of, let's say, very high density, low temperature, or just significantly high density, that's basically it. At some point, we're really dominated by degeneracy effects. So the pressure is supplied by the degeneracy pressure of electrons and or / nuclei. The electrons are typically the more important thing. That boundary condition to this regime is this orange one here. Yeah. What we also have, this is a bit less important for our considerations, is that if we go above this line, so we tend to be dominated by a perfect gas if our conditions are cold. If we're going to higher temperatures, then radiation pressure, which is proportional to T to the 4, becomes more important. Yeah. Now what happens, whether we're radiation dominated or dominated by a perfect gas with pressure proportional to rho T, is really very much irrelevant now in this consideration, because as I said, this approximate direction of the trajectories is really the same whether or not your pressure is supplied by non-relativistic perfect gas or by radiation. Yeah. So what actually happens for stars of different mass is, well, the higher the mass, the higher T will be, the temperature will be for a given density on this trajectory of the central thermodynamic conditions, right? And as they move through stellar evolution, the stars move over towards the right, more or less diagonally. And eventually the low mass stars have the chance to hit this boundary this transition line here, where the degeneracy pressure takes over. Yeah. And once degeneracy pressure takes over, the thing is that at this point, contraction really stops. So the star, if it cools down, does not lose any more pressure, and it's halted from further contraction. Yeah, so for this reason, the stars of, let's say, well, if they're significantly less massive than our sun, then they already stop contracting on their way from star formation before they even ignite hydrogen burning. Yeah, and stars like our sun, well, our sun after hydrogen burning will still contract further and actually ignite helium burning, but then its core will eventually be significantly degenerate, that to stop it from further contraction, and it will not contract any further to ignite carbon burning, and rather stay at constant density and cool down and end its life as a white dwarf. Yeah. So for the low mass stars, depending on how massive you are, you might never ignite hydrogen burning at all, ending as a brown dwarf, or you might end as a helium white dwarf if you just go beyond hydrogen core burning. If you might end up as a carbon white dwarf if you become degenerate enough after core helium burning, or in some cases, this is a scenario where it's actually difficult to ascertain how often and whether that really happens. If a relatively low mass or medium mass star manages to ignite carbon burning and then is prevented from further contraction, it might end up as an oxygen neon magnesium white dwarf. Okay. Now, once you start carbon burning, then it's almost guaranteed, almost, I emphasize almost, that you will remain non-degenerate for the subsequent burning stages. So you will be able to ignite neon burning, oxygen burning, and silicon burning, form an iron core. So silicon will leave an iron core. And after forming iron at the core, you can't do any further nuclear reactions that generate energy. So the star will then contract further and run into an instability that makes it collapse to a neutron star. How that actually happens is something that I'll leave to tomorrow's lecture, because that's really where we go to the supernova scenario. There is a tiny little window of opportunity for the star to ignite neon or oxygen burning and then still do something different. I'll come to that a little later. This would be known as electron. These would be known as electron capture supernovae. They might just happen in the case of single stars in a narrow window around 9 solar masses. If you're more massive than 9 solar masses, you're guaranteed to go through neon, oxygen, silicon burning without hitting degeneracy, form an iron core, and then you collapse. That's the normal core collapse supernova route. If the star is very massive, though, so for single stars, that regime is entered at about 100 solar masses. It will, as it contracts and moves to higher temperature, it will reach a region where electron-positron pairs can be formed. And as a result of the formation of electron-positron pairs, what happens, and now I move over to the summary slide, what happens is that this leads to a drop of the adiabatic index below values of 4/3. Now, an adiabatic index of 4/3 is a stability threshold, or an instability threshold rather. So in that regime, you can hit a pulsational instability, due to these changing thermodynamic conditions associated with pair creation. And that instability can take two forms depending on the mass of the star. So if you're a bit about this minimum mass for this instability, what will happen is that after carbon burning, you'll develop an instability here, and that instability will sort of push parts of the star occasionally into very violent oxygen burning, and that will lead to pulses that expel part of the envelope. Multiple pulses, and the star may do that. The star may do that several times and get rid of some mass and actually decrease its core size so that it eventually gets away from this instability region again and ends as a normal core collapse supernova eventually, where it then goes through oxygen and silicon burning in the core and then collapses. Yeah. If the star is yet more massive, then it can end its life either with one big pulse that explodes the star. This would be known as a pair instability supernova, or the pulse instability might lead to black hole formation for even higher mass. Yeah. So for if you have these pulsations that are not so violent as to disrupt the entire star, but shed only part of it, that will be called a pulsational pair instability supernova. In this regime that involves pair instability is something that I'm not going to cover today. I'll come back to that during one of the lectures later this week on supernova phenomenology. All right, this is probably a good time to allow for a few questions again. What would be the exact concept of degeneracy? Yeah, so you might know, I might do that by interactively switching. Let me do that here. We have a whiteboard here. Can you see, oh, blackboard? Can you see that blackboard? Yes.
Yes, we can see that.
Okay. So, oops, my tablet. Let's turn the wrong way around. So normally what you have, so let's think about the equations of state that you know, right? So for a perfect gas, what would be the equation of state? Let's only use proportionality signs to make things easier. Yeah. So for a perfect gas, we have P proportional to rho T. Yeah. For a radiation dominated gas, we have P proportional to T to the 4. Yeah. And how do these relations come about from the microphysical point of view? Well, what you do is you'd say you actually have your constituent particles, photons or atoms or ions moving around. Yeah. And so, I mean, for the perfect gas, you have your Maxwell distribution of the kinetic energies of your ions and nuclei, and then you get the pressure as basically an integral over the distribution function, the local distribution function. Or pressure tensor. So you'll get something like a pressure tensor as an integral over the distribution function times the particle velocities. Yeah. Now, if you have degenerate matter, I hope you've encountered this at some point. Yeah. If you have degenerate matter, then the particles are so close to, the constituent particles are so close to each other that Pauli blocking becomes important. Yeah. And even at T equals 0 or T equals small, your distribution function will have particles at finite momentum. Yeah. So even at T equals 0, you have particles at finite non-zero momentum because the Pauli principle doesn't allow them to occupy, have the same momentum and and location. Yeah, and that implies that so P non-zero even for t equals 0. Yeah, and for t equals small, P does not depend much on temperature. Yeah. And rather just depends on the density, because the density determines how far you need to spread your particles. So we're mostly concerned with degenerate electrons, how far you need to spread them in momentum to comply with the Pauli principle. Yeah. So, and as a result, in this regime, you have a pressure that just depends on density and does not depend on temperature. Yeah. Does that explain it? Yes. Okay. Now let's go back to the main slides. All right. What further questions? Do we have any further questions on this diagram in these regimes here? And where did the chat go? Okay. Well, you've had some time to put, okay, one more. Yes, so someone mentions that sometimes finite temperature corrections to electron degeneracy pressure come in. That is indeed very important. Yes, yeah. Mm-hmm. And someone mentions when it is important. So I can give you one example. So in the supernova scenario, what we'll have is we'll become degenerate about here after silicon burning. Yeah. However, the ion core after silicon burning will not be completely degenerate. And the ion cores from the more massive stars will still have higher entropy, and that entropy will lead to finite entropy, will lead to corrections to the degeneracy pressure. And that implies that the higher the cores of massive stars with higher mass will actually have ion cores that are a bit bigger than you think might be allowed to remain stable. So we'll get into that in the next lecture. You'll certainly have heard about the famous Chandrasekhar mass for white dwarfs, which is about 1.4 solar masses. That's about also the stability limit for the ion core, the degenerate ion core of a massive star. And that's true for, let's say, the ion cores of lighter massive stars, roundabout. But if you have an ion core of a more massive star with significant entropy, the corrections to degeneracy at finite temperature will imply that these ion cores can become more massive before they collapse, 1.5, 1.6 solar masses, and so on. Now, there was another question about the channel around 9 solar masses. Any exceptions where this value of 9 solar masses varies? Yes, it actually does vary a bit. So this number of 9 solar masses depends a bit on the metallicity, the initial content of heavy elements of the massive stars. This goes up and down as stars become more metal-rich a bit, but it stays round about there. There was work on this a few years ago by Ebeling and Heger. And of course, all of these numbers are numbers for single stars that have not interacted with a binary companion. We'll actually get to this channel in a bit more depth later today. All right. I think we should probably proceed in the interest of time. All right, so
audience here. Hi, Bernhard.
Yes.
Actually, a remark. In the TQ by rho curves, you you made a statement about being proportional to m squared.
Yes.
I think going by the tutorial problem shouldn't be that be m to the power half, although it doesn't change a lot.
Yes, that might be, yes. Yeah. Mm-hmm. That might be, yeah. Mm-hmm. Yes. Mm-hmm. Yes, yeah, you're correct. Yeah, there was a typo there. Yeah, if we spot any typos, we'll upload these in the lectures. We'll upload revised lecture notes later on, of course. Okay, so yeah, and of course the evolution of massive stars is the qualitative features are something that I guess you all know. So once after a certain burning stage, you've exhausted the nuclear fuel in the core, what has to happen is that the core contracts. The contraction will be stopped once you can ignite the next burning stage. And in the surrounding shells, of course, temperatures rise, and that allows further burning stages to be ignited in shells around the core. Yeah, so as you ignite, it's actually not always completely synchronized, but when you move forward beyond hydrogen burning to helium burning in the core, you can then ignite a hydrogen shell also around the core. Yeah, and that goes further with the subsequent burning stages. Yeah, and there are also consequences about these changes in burning in the core for the envelope, at least for the first few phases of nuclear burning. So, okay, we go here. So after hydrogen core burning, what happens is that as you ignite, as the core contracts, the envelope expands. There is a mirror principle in stellar evolution that tends to give this reaction, and the star becomes a red giant, and then eventually red supergiant. Yeah, and it stays that for most of the remaining part of its evolution. It might still move around a bit in the Hertzsprung-Russell diagram, so it might not stay a red supergiant. It might do some excursions to the blue, which is related to somewhat of a contraction of the envelope. That can happen for various reasons. Can happen, for example, if you have mass transfer from a companion, or if the star actually sucks up, swallows a companion. And in the famous recent nearby supernova 1987A in the Large Magellanic Cloud, people very strongly think that this is actually what happened and what made that particular star explode as a blue supergiant with a relatively compact envelope. Yeah. The nature of how the nuclear energy gets out of the star will change somewhat as you go to the later burning stages. That will become important very soon. So usually, so for a star like our sun, the bulk of the energy generated by nuclear burning is carried away by photons. It's diffused to the surface and then radiated away. For the advanced burning stages in massive stars, at some point, the energy is lost directly, radiated away directly by neutrinos, and photon diffusion becomes unimportant. This is also related to another very characteristic phenomenon in terms of the stellar structure of massive stars. So these advanced burning stages, and I'll give you an illustration of that, usually tend to burn convectively in such a manner that, maybe a little sketch is in order here, that if you have a shell, yeah, where something burns, yeah, so you have here basically nuclear energy generation input, stuff will get buoyant, yeah, and it radiates away neutrinos really from everywhere, yeah, so neutrinos go out, and the energy is lost through neutrinos, and you have sort of a cycle where at the bottom of a shell, you have the strongest input of nuclear energy generation by heating, and then that drives convective turnover motions, and throughout this convective region, energy is lost by cooling into neutrinos. Yeah, and the whole shell remains in a balanced state between the energy injection by nuclear energy and the transport of energy around by convective motions and the loss of energy by the cooling of neutrinos. And that has important consequences for the structure, which we'll see in very shortly in plots. Yeah, incidentally, but for a slightly different reason, the core burning phases, the early core burning phases in massive stars also are convective. So above the shell where most of the burning happens, region where most of the burning happens, these drive convective motions. And this structure of a star with different shells of different composition and convective motions driven by nuclear energy generation and neutrino cooling, that is best visualized by what is known as Kippenhahn diagrams. Maybe, or hopefully some of you have seen something like that before, but even if that's the case, it's good to be reminded about that. So those Kippenhahn diagrams show the composition of the star, the shell structure, as a function of time here on the x-axis. Yeah, and you see marked in these diagrams where nuclear burning happens, that's in blue, and where neutrino cooling dominates, that's in purple. And these greenish regions, that's regions that are convective. And what you always see is these late burning stages here, they have very thin bluish regions at the bottom. That's where the nuclear energy is generated. And then they drive convective shells above them. And further out in those convective shells, neutrino cooling dominates. Yeah. And the sequence of those shells can be quite non-trivial. So it's easy. Early on, you have hydrogen burning in the core that starts, then you start helium core burning. A shell is emerging at about the same stage. And then you might have some periods of quiet in between, and sometimes a shell burning, like this helium shell burning here, starts before the next burning is ignited in the core. The carbon burning, similarly, this carbon shell burning episodes that burns a bit of a bigger part of the inner regions of your star starts before you burn the neon. Yeah. And then the sequence of shell and core burnings might become quite a bit chaotic. Yeah. In the core, the sequence is clear. Helium, hydrogen burning, helium burning, carbon burning, neon, very short here in the core, oxygen burning, silicon burning. But the silicon burning in the core is actually not the end. Before this whole thing will actually collapse to an iron core, you do another silicon burning episodes in a shell, and then some oxygen burning at collapse to make this core grow even a little bigger. And only then after a while do you collapse. Yeah. Now questions about these kinds of diagrams.
Hello, can you hear me?
Yes, I can.
So I couldn't quite follow how the evolutionary path of so I can't read the axes first of all. So is that time on the?
So there you have log time until collapse on the x-axis, and you have the enclosed mass on the y-axis.
So this is enclosed mass of what exactly?
So this is the entire, so basically you think of this as a different radial coordinate, yeah? So you label the position inside your star as the entire mass inside a certain shell, yeah? Mm-hmm. So if your star looks like this, now these might not be real shells, but you might label this particular shell here, yeah? So that's labeled, that shell is labeled by m equals 4 pi r squared rho, r prime squared rho, dr from 0 to r. Yeah. And inside this shell here, yeah, you have more mass, yeah, and you label that by the bigger mass inside this shell, yeah. So if you haven't encountered this before, just think of it as an alternative radial coordinate, yeah. And it has the advantage that I can always label the same shell with the same mass coordinate as the star expands or contracts.
Correct. Okay, thank you. Yeah, that's clear.
Yeah. Then there was another question. Why does the outermost layer of hydrogen expand as the star progresses further in its lifetime, irrespective of giants, supergiants? I don't quite understand that question. Can you maybe rephrase that a little bit? So what does irrespective of red giants or supergiants mean here? In general, well, actually, you pose a very good question. The thing is really, the only thing that we firmly established in stellar evolution is that there is this sort of mirror principle that when the core contracts, then the outer shells tend to expand. But people have actually struggled a long time to tie this to a single physical principle. And there is not a single physical principle that explains why the expansion happens. People have struggled for a long time, but the only thing that's really a robust statement empirically is that there is a sort of mirror principle. As the core expands, the shells outside it tend to expand. And the core always has to, as the core contracts, the shells outside it tend to expand. And the core always has to contract because that's the only way you get to, well, after the hydrogen is exhausted, the only way for it to go forward, for the core to go forward and again become stable is to contract until you hit a further burning stage. And then you get an energy source that can again keep the star in thermal equilibrium and keep it from further contraction. Yeah. So it's the unavoidability of the contraction of the core and the mirror principle. But as I said, the mirror principle doesn't always hit. So if your envelope is very small, for example, yeah, then the stable structure might not be a red supergiant, but it might be a blue supergiant. Yeah, that's very tricky to explain the exceptions to evolution towards a red supergiant that might occasionally happen. All right.
Hello, Professor.
Yes.
From the previous diagram, the previous
Yes.
showed the previous
Yeah.
one.
The previous one. The previous one.
OC and TC graph. Yeah.
Yes. Yeah.
Can you explain like how and when this rapid electron capture happens, and also like what do you mean by this relativistic instability?
Yeah, this relativistic instability really means that's the instability. Yeah, okay, that goes perhaps too long a way to explain now. Especially this rapid electron capture here. I think I'd like to defer that to later because I have a few slides on that. This relativistic instability, what this actually means is, well, that's essentially the Chandrasekhar limit. That's what we mean. So at some point, as the star contracts, the degeneracy pressure does not increase fast enough to make up for the stronger gravity with the contraction, and that's why an instability occurs. Yeah. So basically, this instability, to phrase it in very, very simple terms, perhaps a bit oversimplified, is that over here, what happens is that the degeneracy pressure simply doesn't increase fast enough as you compress the star to prevent gravity from taking over. That's a bit oversimplified, but doing the entire calculation would take us a while. Okay, good enough for now. I should probably also say that, yeah, because we're bringing people with very different backgrounds together, what we should probably do is we should also, so if there are deeper questions that you feel to go back to sort of what I'm assuming, what might be textbook knowledge for someone, but not for others, we could also have a longer discussion of course, in the tutorials. Now, here I just want to show you quickly what this balance of between nuclear energy generation and neutrino cooling means in convective shells. So this is a function of this mass coordinate. The nuclear energy generation rate in black, the neutrino cooling rate in red, and the blue curves denote how fast the convective motions are going up and down at a certain shell. Yeah. So what you see is here for a silicon shell and an oxygen shell, nuclear energy generation rate is strongest near the bottom of the shell. Yeah. Neutrino cooling is also strongest there, but it has less steep temperature dependence. So it tends to be dominated by the nuclear energy generation rate at the bottom. And over the entire shell, this area, so the total energy generated by fusion or lost into neutrinos is about the same. Yeah. And the convective motions distribute stuff around to shuffle it around from the region where energy is injected by nuclear burning through the entire shell to ensure overall balance between energy generation and energy losses. Now, this balance of power between nuclear energy generation and energy losses is basically what sets the characteristic shell structure and determines where certain nuclear and when certain nuclear burnings occur. I already hinted that the nuclear energy generation rates have a very, very steep temperature dependence. If any of you have a nuclear physics background, the reason for this is really that the nuclear reactions occur from particles that are in the very tail of the thermal distribution of kinetic energies. And that introduces an exponential dependence into these rates on temperature, whereas the neutrino losses tend to depend on a moderately high power of the temperature. So if you have neutrinos from the annihilation of electron-positron pairs, the temperature dependence will go about with T to the 9. That's still moderately high, but not nearly as high as the energy generation rate. So if you want this balance of power in these convective burning regions, what you'll have is that essentially you'll have to hit your steady state of a burning shell is determined by the intersections of these steep curves for the nuclear energy generation rate and the neutrinos, and that fixes the burning temperatures to a to a rather robust threshold value, and it also fixes the equilibrium entropies, and together with the structure equations, the equilibrium temperatures and densities of the shells. And if we go back to the Kippenhahn diagram, the way this balance is enforced really is if you had just a bit of an excess in nuclear energy generation rate, then the shell would expand, and as the shell expands, the temperature will just drop slightly and the nuclear energy generation rate will drop slightly, and that will bring you back into this equilibrium. It doesn't take a lot of expansion to get you back into this equilibrium, because of the steep temperature dependence of the nuclear burning rates. Yeah. The bottom line of this is that the shell structure of massive stars, it may seem very chaotic, but there are really understandable physical principles involved. So what I'm showing here is are two plots of density profiles and entropy profiles of massive stars of different initial mass. And it might be useful to look at the entropies first and the densities later. So you'll actually still see in these entropy profiles this trend of massive stars having higher core entropies that carries through to the very late stage before collapse of the iron core, which you see here. Yeah, and this balance of power between nuclear burning and neutrino losses basically fixes the previous burning stages, the other burning stages, to certain entropies, and that gives rise to a characteristic step-like structure in these entropy profiles. Yeah. So, for example, if you have some experience with this, you can usually identify that this one here, yeah, at about an entropy of 5 or 6, that's where the oxygen burning happens. Yeah. And this here tends to be the helium shell. Yeah. Convection will tend to flatten out entropy gradients as it mixes material. So the convective shells are seen as flat regions in these profiles. Yeah. And in between you have inert shells where no burning happens. In terms of what this means for the density structure, so basically the thermal structure of the star will dictate through the condition of hydrostatic equilibrium what the density structure will be. So these shells here, so the interfaces between the shells, that's where entropy jumps, and a jump in entropy, yeah, from colder to hotter material in terms of entropy will mean that there can be a step in density as well. Yeah, and this is simply due to the fact that, let's say, if you have P, so for a radiation-dominated gas, you essentially have entropy proportional to T cubed over rho, and that means that the pressure, which is proportional to T to the 4, that's related to rho S to the power of 4/3. So if P is supposed to be continuous, so pressure continuously decreases as you go out, this means that any discontinuity in S means in hydrostatic equilibrium, you get a continuity in rho. Yeah, because the pressure is continuous as you go further out through the star in hydrostatic equilibrium. Now, the consequence of that is that you get at shell interfaces, you get these steps in density. And the entropy profiles really determine your density profiles at the end of the life of a star as it collapses, before it collapses. Why am I focusing on this so much? And I have to warn you, I have to skip a lot of analytic theory that goes into this here. The reason why I'm dwelling on this is because the pre-collapse density structure is very important for determining the collapse, the dynamics after the collapse of the iron core and during the way of the stellar core to a supernova. Yeah, basically what the pre-collapse density structure dictates is it dictates the rate of mass accretion onto the young neutron star or the supernova shock around it after collapse. And this mass accretion rate is a central parameter for the dynamical evolution of the supernova. It's sort of it dictates how much of an accretion temp, as people sometimes call it, how heavy a lid you have on the supernova shock that might keep it from expanding. Yeah, this is an important takeaway, this relation between the pre-collapse density structure and the mass accretion rate after collapse. So the best way to judge what is going to happen with a star is really to look at the after collapse to a neutron star or a black hole, whether you explode or not. The best way to decide is really to look at the pre-collapse density structure, short of doing a full supernova simulation. Very often people, however, find it useful to look at even simpler global parameters. And there are several global parameters that you can use to quantify how explodable a certain star will be. And the key realization is basically, well, it's all going to depend very much on how much density you have outside of in the vicinity of your iron core. Yeah. So these low mass stars, a 12 solar mass star here, for example, with a more precipitously declining density profile, will be easier to explode than these more massive ones here. And there are various parameters, global parameters, that you can use to approximately quantify that. So you could think of, let's say, the density outside the silicon iron core, or you could talk about the size of the silicon iron core in terms of mass. A very convenient parameter empirically is this so-called compactness parameter, which is basically the ratio of a certain reference mass coordinate. People very often use about 2.5 here, and the radius where this mass coordinate sits normalized by 1,000 kilometers. Yeah. In essence, what this parameter tells you is really, to boil it down to the essence, is how much mass is there, or how dense is the star in the vicinity outside the iron core. Yeah, that's what this is sensitive to. And now I'm accelerating a little bit because I think this lecture might not go as quickly as I imagined, but then we just continue this maybe tomorrow. The interesting thing now to take away is that very generally, what you get as a result of this relation between central entropy and mass that we have discussed at the very beginning is that stars with higher initial mass tend to have bigger iron cores. They tend to have a bigger compactness parameter. They tend to have more massive envelopes outside the iron core and so on. Yeah, that's a general tendency, but this dependence is not completely monotonic. Yeah. So if you look at the dependence of this compactness parameter, which is an often used parameter for the explodability of massive stars, you'll find it has a very non-trivial structure. It tends to increase systematically up to about 15 solar masses. And there's a lot of chaos here going on. And you get a big peak of this compactness parameter at about 20 solar masses, and then it decreases again and starts to increase again at about 27 solar masses. Incidentally, in this diagram here, this is from an analytic study of where we look at what the fates of these stars are going to be. So red means we think they explode, and black they form black holes, and blue might be something in between, which we call fallback. But that's probably a bit of a detour here. Yeah, but the bottom line is that stellar structure in certain regions actually depends quite non-monotonically on initial mass. And the reason for that is, or there are various reasons for that mass. On the one hand, if you look back at the Kippenhahn diagrams, On the one hand, this basically comes from stochastic variations in the sequence of these burning shells. Yeah. So if you go slightly higher in initial mass, you might ignite the burning shells in a slightly different order, and that affects the iron core mass at the end. Or you might have some of these burning shells merging with each other, and not in case of a massive star of very similar mass. And that gives rise to stochastic variations like the ones that you have here. Yeah. But there are also systematic effects that give rise to the macroscopic structures of the landscape of pre-collapse stellar parameters. And a very important one is the one responsible for this compactness peak. So this compactness peak has actually been identified as due to a transition in the way how carbon burning is ignited. So below about 20 solar masses, the carbon tends to be ignited in the form of convective burning. Above 20 solar mass, the carbon burning in the core starts non-convective, and that imprints longer-term differences on the shell structure that give rise to this peak in compactness, or we would also see it as a peak in pre-collapse iron core size, and so on. Okay, this is maybe another point where we can quickly pause for questions. I'm going to switch on some lights.
Can you hear me?
Yes, I can hear you.
Yeah, so why this cooling mechanism is predominantly neutrino cooling?
Because that's the reason is that the neutrinos actually go out freely without interactions. Yeah. So if you have something here, oxygen, carbon, or carbon to oxygen, oxygen to silicon. The reason is that the neutrinos go out without any interactions, whereas the photons would need to diffuse slowly in this dense material. Yeah. So the neutrinos stream out freely. Yeah. So whenever the matter is hot enough to emit neutrinos in copious quantities, they will be responsible for cooling or carrying away the energy generated by the nuclear reactions. Why does this not happen in a star like our sun? Well, the reason is simply that the interior, it happens to some degree, and we can actually measure the solar neutrinos that come out of this, the burning region in the sun, but it does not carry away that bigger fraction of the energy because the temperatures in our sun, central temperatures, are smaller than what you encounter in the advanced burning stages of massive stars. Yeah, so you simply don't make as many neutrinos by these processes here. E plus, E minus goes to nu and nu E bar. Yeah. So for pair creation like this one, you need high enough temperatures to actually have the electron-positron pairs around. Yeah. So does that answer your question?
Yes. Yes, yes.
Yeah. Then I should probably plow on ahead. So one very important thing to realize about the, and this is actually connects to the neutrino cooling that you mentioned. One very important side effect of neutrino cooling taking over is that the advanced burning stages after helium burning happen very quickly, much more quickly than the previous ones. So helium core burning still takes about 10% of the lifetime of a massive star. All the rest basically happens in no time because the energy generated by the nuclear reactions does not need to slowly diffuse to the surface for the star to reach some internal thermal equilibrium. It gets out immediately. Yeah. And as a reason, the late burning stages are very, very short. Yeah, so still thousands of years for carbon burning, but then you're talking about timescales of years, months, or weeks. And for some of the shell burning episodes, you're actually talking about timescales of hours. Yeah, and as a result of this, you basically see we very strongly think that you see no effect of what's happening during the very latest burning stages on the surface of the star anymore, simply because these processes happen so fast that the envelope cannot adjust anymore to any changes in the interior. Yeah, and conversely, changes, well, the envelope is basically, the interior core of the star basically just sees the envelope as a constant weight that it has to carry, and the envelope and core of the star, in a manner of speaking, don't talk to each other anymore. Yeah, that has an important side effect. So if you lose, let's say, your hydrogen envelope after helium burning, then the evolution of the star will just be the same as for a star with a hydrogen envelope, but with the same mass of the carbon-oxygen core that was formed after helium burning. And to a lesser degree, you can argue, but that's a bit more shaky, you can argue that once the helium core mass of a massive star is fixed, then regardless of how you lose the hydrogen envelope, this will not make too much of a difference for what's going on inside. There is actually still a difference if you lose your envelope after before helium burning is finished. If I have time, but that might take until tomorrow, I will actually briefly get to that. Now, this brings me to several factors that actually influence how, or might influence how we go to collapse, and what the pre-collapse stellar structure is in terms of ion core mass and this compactness parameter and so on. Yeah. So mass, there are various factors that affect this. And one of them is, well, to what extent do the stars lose mass? Yeah. So if you lose mass early on, yeah, during the main sequence, or before helium burning is finished, right? So early enough, this will still affect the structure of your star at collapse. And you must bear in mind, and I probably need to be a bit more superficial in this part of the lecture, this will create systematically different outcomes on stellar evolution, depending on what environment you live in. So whether your star was formed with high metal content or low metal content, and whether your star interacts with in a binary with its companion or not. So at solar metallicity, the winds will eventually make the star lose mass. Yeah. Winds, we think, stellar winds, we think, lose mass more effectively at higher metallicity. There are still some questions to be sorted out in detail, especially when it comes to stars that have actually lost their hydrogen envelope and have laid bare the helium shell and are known as what we call Wolf-Rayet stars. There, the precise metallicity dependence is a bit more tricky to work out, but this does not really matter too much for our purposes. But let's just look at the overall impact of mass loss on the final fate, or at least on the final structure of massive stars, as affected by wind mass loss, supposing that the star is a single star that can only lose mass by winds. So with our current understanding of stellar mass loss rates, what we think happens is that stellar mass stars from massive stars will lose a fraction of their initial mass as they evolve towards collapse. That's not a big deal if you start close to the threshold. So at 9 solar masses, 10 solar masses, where you just start to make core collapse supernovae. But when you go to higher masses, 15, 20, 30 solar masses, mass loss would be more substantial. And we think that stars with sufficiently high initial mass might actually lose eventually all of their hydrogen envelope, turn into what I said are Wolf-Rayet stars. And these Wolf-Rayet stars, these stripped stars with no hydrogen envelope, would actually make different types of supernovae observationally than the lower ones, which still have the hydrogen envelope. This will be the subject of another letter. And the relation between the initial mass and the final mass before collapse will actually be non-monotonic in solar metallicity environments because of this wind mass loss. So the higher mass stars will actually end up with lower mass at collapse. That does not necessarily mean a lower mass of the core, but to some extent that might even also be true. And this entire diagram is now very complicated, and the details are from the Woolsey-Hager-Weaver review, and some of the details may actually be outdated somewhat by now. What I just wanted to flag is really the importance of mass loss on the evolution of single stars here. A few explanations here. So RSG here means red supergiant. So if you actually want the full explanation of this diagram, I'd actually refer you to the review paper directly. As I said, not all the details are important. I just wanted to highlight that mass loss is an important parameter for single stars of high masses at solar metallicity. If you go to low metallicity environment, you might get into a regime where mass loss is in single stars is not very pronounced, and you can retain very high masses of stars at collapse and make stars with very massive cores also. And the implication of that is, and now let's go to the summary slide. The implication is that certain types of collapse events might actually only happen in low metallicity environments. So those that require stars with very massive stars with very massive cores to be around, those might be confined to low metallicity environments. And for that reason, we might this channel of pair instability or pulsational pair instability supernovae might not actually happen in the local universe in solar metallicity environments. Other channels of certain special supernovae that probably come from more massive stars might at least be suppressed very strongly. So this difference in mass loss rates may contribute, for example, to our not seeing very many supernovae with gamma ray bursts in the local universe. These also tend to cluster towards lower metallicity. So incidentally, I'd like to highlight this part of the lecture is a bit more phenomenological than the rest, a bit less mathematical, less quantitative. And here you'll find a lot of information that you just pick up for now, and perhaps it's a bit undigested, but it'll help you, let's say, trigger a certain memory that there might be something interesting in if you ever stumble across supernovae and their explosion mechanisms and their outcomes in any of your research projects. So if you don't understand all of that part in full, don't be worried about that. Now, mass loss by wind is not the only mechanism that can change the pre-collapse structure of massive stars. The other mechanism for mass loss that plays an important role is mass exchange in binaries. This can mean that the star loses mass to companion. It means that it can accrete mass for the companion, or that you might have a merger in a binary star. Yeah, and based on statistics, we have recently realized in the past few years that binary evolution is important for understanding supernova progenitors. We know from statistics, or counts of populations, that a large fraction of massive stars will interact with a companion during their lifetime. And we also know that we actually do not have enough massive stars, sufficiently massive stars around to form enough Wolf-Rayet stars to account for all the supernovae that have no hydrogen in their spectrum. So this makes us think that many of the supernovae which seem to have lost their hydrogen envelope actually have lost this due to interaction with their companion in a binary system. And this mass exchange in binaries can have various impacts on the subsequent evolution of your star. The most important, most prevalent case, which is mass loss due to a companion. The outcome of that depends very much on when you do that mass exchange. So do you do it while the star is still on the main sequence? In this case, in the study that I'm quoting here, we'd actually have that on the late main sequence. Do you do it as the star is moving to the red giant branch or on the red giant branch in case B, mass transfer, or do you do it after helium core burning in case C? And what you basically see here is just an illustration that binary mass loss can actually have a significant effect on the stellar structure at collapse. So if you transfer mass by case A or case B mass transfer, so before core helium burning is completed, you will see that this dependence of the final core compactness on the mass of the carbon-oxygen core after helium burning is changed systematically of the orange and light blue ones here compared to the dark blue ones here. And actually you have a wider range of stars that have low compactness and are better explodable in case of case A or case B mass transfer. Yeah, so this is just the bottom line of all of this is actually mind the effect of mass transfer in binaries on the final pre-collapse structure of massive stars. Yeah, if you don't have time to dig into the details, but just be aware that this is important. Yeah, so I should probably quickly touch base with the organizers. I have actually a few more slides that I should probably cover, and in the last slides, I can actually move into the nucleosynthesis lecture. How much, we've already run over a little bit. How much time do I still have?
That's okay. You can take a few more extra minutes.
Yes, okay, that's very nice. Yeah. So, yeah, to wrap up, I should probably talk a bit about the uncertainties of the structure of massive stars prior to collapse. Yeah, I already mentioned mass loss, mass transfer. So also the single star mass loss rates are still beset with somewhat large uncertainties. Mass loss by winds is a very difficult problem. Yeah. The binaries are a known effect, but there are also effects on the internal structure of massive stars that are still uncertain. Yeah. So, for example, in stellar evolution models, we need to treat processes that mix material that are genuinely multidimensional, like convective turnover. We need to mix that, to treat that by some effective 1D model, basically by using some form of diffusion equation. And to what extent that captures these mixing processes is not always clear. It does a very good job for some aspects of convection and similar mixing processes, but maybe not for others. Similarly, we as I said, stellar stars generally rotate. So we also need to treat the transport of angular momentum within stars and the loss of angular momentum. Now, rotation is, again, a genuinely multidimensional phenomenon. And what we are doing in state-of-the-art models of the evolution of massive stars, you treat that angular momentum similarly in spirit to how you treat convective mixing or other mixing processes. So you throw in some form of diffusion equation or advection diffusion equation to prescribe the effect of, let's say, redistribution of angular momentum by convection, by shear instabilities, by magnetic stresses, and so on. Yeah, you can derive the transport coefficients that go into that diffusion equation. You can motivate that, but there's always the question, does it actually describe the physics accurately? Yeah, and especially as far as stellar rotation is concerned, it's a big challenge to reproduce, on the one hand, angular momentum transport in such a way that your low mass stars look like the low mass stars whose core rotation rates you can measure by astroseismology, and that your stellar evolution models will give you the correct spin rates of white dwarfs, say, and these tend to be very slow. And on the other hand, that treatment of angular momentum still needs to allow for some stars to rotate very rapidly at collapse, because that's the only way we can imagine certain hyperenergetic supernova explosions to occur. Yeah, and that's a big challenge. Now, to show you a bit what we're doing on that front at the moment, so to better understand the physics of stellar mixing and / angular momentum transport, what we can do nowadays is to selectively conduct multidimensional simulations of select short phases in stellar evolution. And then the challenge is to project that back to the evolution of entire stars. Yeah, and we know, for example, that convective motions shortly before collapse will actually have a big impact in the supernova explosion mechanism later on. That's something that we found in recent years. But simulating the evolution of massive stars over long timescales, of their entire lifetime, is just not feasible. So that there's a challenge in projecting back to the 1D stellar evolution models there. And in order not to create a false impression, we do not think currently that, let's say, the treatment of convection is fundamentally flawed. So what we do in 1D stellar evolution models gives us a correct estimate of the dynamics inside convective shells, but it's much less clear how well 1D stellar evolution models treat the evolution of convective boundaries, where there might be extra mixing going on. And to some extent, 1D stellar evolution models show that mixing. So in some of these Kippenhahn diagrams that I showed you of massive stars, what you will find is that as the shells evolve, they actually merge with each other sometimes. And the question is, though, whether 1D stellar evolution describes such processes correctly, whether they might occur much more frequently in nature or so. And for that reason, people are doing real 3D simulations of these processes that show you, in this case here, how the boundaries between convective shells can be eroded by turbulent fluid motions, and then the shells merge dynamically. Yes, so what you see in this diagram from the Yadav paper here, for example, are indicators of convective stability. Blue is stable, red is unstable. So the red regions were convective before, and there are barriers between the convective regions, blue barriers, and that gets eroded at some point. And then these entire two shells here, this is an oxygen shell and a neon shell, are mixed on very short time scales. Yeah. Now, all of this final stuff of this lecture, to mind you again, that's more of an outlook on current research, right? So if you feel, don't worry if you might feel a bit lost on that. This is just about flagging important research questions at the moment. About the treatment of angular momentum transport, what the current stellar evolution models do is they actually predict spin down of massive stars that are about compatible with what we need to explain the birth spin periods of neutron stars of a few tens of milliseconds. But if you try to compare the input of that we currently have, the prescriptions that we currently have for angular momentum transport by magnetic torques, if you compare that to evolved low mass stars where we can measure co-rotation rates from astroseismology, you'll find that the current treatment of angular momentum transport still doesn't give you enough spin down of the cores of evolved stars. So there's a question here, what's going on and how we can bring our theories and the observations into consistency. All right. Yeah, I think I should. Yeah, I think I'll wrap up with this very quickly because there was a question at the beginning. There was this a question about the special scenario on this channel around 9 solar masses of electron capture supernovae, yeah, where you go beyond carbon burning and then something happens at after carbon burning and the star then collapses different before really forming a hydrostatic ion core. So what really happens there is a core evolution that is actually extremely complicated. So in this diagram, temperature versus density at the center. So what happens after carbon burning is, so you should look at probably this region here. No, this black dashed one here. At some point you have something of a neon flash. So neon is ignited off center, then it burns to the center. Then you have a very complex interplay of neutrino cooling processes and electron captures on neon and magnesium that tend to drive the star towards instability. So a very complex interplay between some nuclear burning going on and neutrinos carrying out energy. And depending on how that competition unfolds, you might end up with a collapse on dynamical timescale, basically, after you ignite a neon flame or an oxygen flame in the core. Yeah. And that would be a sort of distinct scenario towards collapse, because the collapse happens without you ever reaching a hydrostatic ion core. Yeah. Eventually you burn stuff to iron, but during that time, you're already in a dynamical collapse. And this scenario is an incredibly complicated one. It's an incredibly complicated one. It has, however, carried considerable interest because some people believe or have believed that the very famous Crab supernova that was observed in the 11th century by Chinese astronomers might have been such an electron capture supernova. So the name electron capture comes about because what really gets you into collapse are rapid electron capture reactions on neon and magnesium here after the neon burning is ignited off center. And this is a topic of very active research. So when does this occur? Can this occur in single stars, or can it only occur in binary stars? Because that can give you the right core size for this to happen. The interest is also prompted by the fact that this would give you a very special kind of supernova because the density structure of such a star would be very extreme. There would be a very compact core with a very steep drop of the density outside it. And that would imply that you get a low energy explosion. It would imply that your neutron star couldn't be kicked during the explosion. And it would very much fix the mass of the neutron star that you make from this to about 3.7 solar mass is baryonic. But it's a topic of very active research, and we don't know for sure whether that channel is actually realized in nature. But I wanted to flag this as one of the many uncertain problems in stellar evolution. And I think that's a good time to break, probably, after allowing for further questions.
Thank you very much, Bernhard. This was a great way to start the school. We can take a question or two if there is interest.
Thanks. So I had two broad questions. So the first question is, so for instance, the plot that you mentioned about, that you showed about the compactness at 2.5 mSan versus, I guess, the Zamas mass.
Yes, that's.
So is this can you get this kind of plot by some semi-analytic arguments, or do you have to do numerical simulations for this?
Yeah, you actually really have to do numerical simulations for this, because so as I said, what forms these structures here? So this peak here at 20 solar masses, that comes from the nature of carbon core burning. So whether it's convectively stable or unstable, only your stellar evolution model can tell you. And these chaotic variations down here, that's basically from the question whether certain burning shells merge or don't merge, or whether you ignite 3 or 4 oxygen burning shells before the collapse occurs. And again, that's something that only a stellar evolution model can tell you. Yeah. The overall trend, that's something that follows from the mass entropy relation that we discussed at the very beginning. But the structure is something that you only get from stellar evolution models. And I should probably emphasize, because it does look very chaotic, I should emphasize that this is one of the features, one of the structures where the stellar evolution models actually agree pretty well, regardless of what code you use. This will change if you treat the mass loss differently, or if you treat your core hydrogen convection differently on the main sequence. But if you express this in terms of the helium core mass or the CO core mass, the structure will look quite similar for different stellar evolution codes. There's a bit of a sensitivity on the nuclear and neutrino input physics, cooling rates, and so on, but the structure will look very similar, regardless of what code you use.
Yeah, that was going to be my another question, but I have one more question. So what is, can you tell us about about the observation, the way people try to constrain these scenarios by observation? For instance, how do people try to understand the shell structure through observation? Is there a way? I mean, is astroseismology one of the ways?
Okay, yeah, that's a very good question. So with astroseismology, you're a bit, that's actually something that I'm not a deep expert on, but you're actually a bit hard put with massive stars in general. But I do know that for massive stars, there are now constraints on the core structure of massive stars on the main sequence. That's already interesting enough, because there has long been, so there's actually a great sensitivity on the stellar evolution models on the treatment of convection during the main sequence. So how much overshooting you allow, or whether you evaluate convective stability based on the entropy gradient or based on the Ledoux criterion, whether you allow for semi-convection. And that's something where astroseismology is helpful for constraining the core sizes of massive stars. For extra mixing processes and angular momentum transport and so on, astroseismology has unearthed very important findings on red giants. It's not quite clear often how that transfers to massive stars. There are issues, for example, like certain angular momentum transport processes that may occur in a certain mass range for low mass stars and be relevant for the red giant core spin rates might not be universal. So There is a debate, for example, about the role of internal gravity waves in transporting angular momentum. And some of these mechanisms might kick in in a certain mass range, but not in another. Yeah. And that's what complicates the interpretation, but you certainly learn a lot from these observations in general about the understanding of the basic hydrodynamic processes.
Thank you.
Yeah, hi, I have a question about the mass loss affected by metallicity content. So could you sort of elaborate on this, how higher mass loss is corresponding to higher metallicity content in the star?
Yes, so there's really the basic arguments that many of the mass loss processes will be sensitive to the opacity in the envelope. So the presence of metals, the presence of, well, dust in cool red giants and so on. And that opacity, yeah, will increase with a presence of more metals in the star as it was born in general. Yeah, that's how the metallicity dependence basically comes about. But the precise dependence would have to be measured. And there are often debates about whether a certain mass loss prescription should have a dependence on z squared or z to the power of 1/2 or whatever. Yeah, measuring mass loss rates is quite tough. I don't do it. And we understand the basic physical mechanism. More metals mean more opacity, more stuff around where you can scatter in lines, in spectral lines, and that generally will increase mass loss rates. But the precise dependence may be more difficult to work out.
I see. Thank you.
Okay, I don't see any questions further. Thank you very much, Bernhard, for this excellent kickoff lecture. We will continue tomorrow. So for the participants, we are breaking a bit late. So let's aim to come back at 2:15 instead of 2 o'clock lunch. Thank you very much, Bernhard, and see you tomorrow.
Bye.